Hello and welcome to this video, and it is a part of this lecture series on group theory that is being given at Air University, Islamabad, Pakistan. And today the topic of my discussion will be cyclic groups, and I will present the definition, then some examples, and then I'll prove one property for cyclic groups, very important property. And related to this property, I will prove two corollaries of the theorem 4.1. So let's start. Um, let us start with the definition of cyclic groups. A group G is called cyclic if there is an element A in G such that G can be written as the integer powers of A. So A power n such that n belongs to Z is the set. And we call this set as the cyclic subgroup of a group G. But in case if it is equal to the whole group G, then the group G is called cyclic group. Now, such an element A is called the generator of G, and we denote cyclic group G generated by an element A by this notation. So G is a cyclic group which is generated by an element A, which is by a single element A of G, and we denote it by this notation. Let us see some examples. A set of integers Z under addition is a cyclic group, and it has only two generators, 1 and -1. Both of these elements generate the cyclic group of integers under the operation of addition. It is easy to check that 1 is the generator because first of all we know that the group G is of this form, A power n such that n belongs to Z, and it's a group under addition. So we will take, instead of A power n, we will take n A, the multiples of n, or we can say that we will take the sums of A with itself n times, right? So when we say that 1 is the generator, this means 1, first of all, 1 belongs to the group generated by 1. Secondly, since it's a subgroup, so its inverse must also be there. So -1, which is the additive inverse, will also belong to 1. And now if we take any positive integer n, then n can be written as 1 plus 1 plus 1 up to n times, right? So this is when n is positive. But if n is negative, so if n is positive, but what happens if n is negative? Because in integers we have both positive, negative, and 0. So 0 can be, we know that 0 is also there because 0 times A, and it is there because this is a subgroup, so identity element must be there. So 0 is there already. Now if n is negative, then we can take -1 sum with itself up to n absolute times. So we will have absolute n terms in this sum, -1 plus -1 plus so on -1. So similarly, we can prove that -1 is also the generator of Z. So we can say that Z is either it's a cyclic group generated by 1, or we can also consider it as a cyclic group generated by -1, right? So it is easy to prove both the properties, both the definitions. Next example is the set of residue classes of integers from 0 to n minus 1. So we have integers modulo n, the congruence relation defined on it, 0, 1 up to n minus 1. For n greater than equal to 1, this is also a cyclic group under addition modulo n. So we are the operation of this group is addition modulo n. Again, we have these elements 1 and -1 which generate this group. So 1 generates this group because we can have 1 plus 1 plus 1, and 0 is also there because if we take n times, if we add 1 with itself n times, then n times 1 is equal to n, which is congruent to the class of 0 mod n. Similarly, -1, since it is congruent to n minus 1, in the according to the congruence relation defined on the set of integers. So that is why n minus 1 is also the generator of this set Zn. Now, but there is a caution here. These are not the only generators for Zn. Actually, there can be more than one generator. So we have a caution that 1 and -1 equals n minus 1 are not the only generators. The only generators of Zn. In case of integers, yes, there are only two, 1 and -1. But in case of residue classes, these are not the only generators. In the next example, I'll present this. So Z8, you can see that 1 and 7 are the generators according to the last example too. 1 and -1, then it means 1 and 7. These are the generators of Z8. But other than these, we have also the generators 3 and 5. We can easily prove it. 3 when added with itself. So we get 3 plus 3 equals 6, which is there in the Z8. Then if I add 3 plus 3 plus 3, then I get 9, which is congruent to 1, right? Because modulo 8, because if I divide 9 by 8, then the remainder is 1. Similarly, so now I have 3 itself is there, 6 is there, 1 is there. Now what other elements are there? We have 4 times 3, which is equal to 12 and is congruent to 4 mod 8. So now we have 1, 3, 4, 1, 3, 4, 6, and 9. Now what else? We have 5 times 3, that is 15, which is congruent to 7. Then 6 times 3, that is 18, and it is congruent to 2. And so how many elements are left now? 1, 2, 3, 4. And we have 6 and 7. So only 5 is left, I think. Then we have 7.3. If we add 7 3 times, then this is 21. And since this is equal to 5, right? This is congruent to 5. Now we have all the elements which are there in Z8 generated by this element 3. Similarly, we can also prove that 5 is the generator of Z8. So it generates all the elements of Z8. So these calculations you can verify yourself. First of all, I should take 3. Then I have 1. Then I have 2, 3, 4, 5. Here we have 6 and 7. Yes, so all the elements are there generated by 3. Similarly, we can prove that 5 also generates Z8. Now, if I talk about U14, we have denoted as you remember, if you remember from the last few lectures from my other videos, that U14 is the group of complex is a group of integers less than 14, and they are relatively prime with 14 under the multiplication modulo 14. So what are the elements in this group? U14 contains these elements. So since they are, it contains 1, It contains 3 because 3 is relatively prime with 14. It contains, it do not contain 4. Now it has 5. It has 6, no, 7, no, 8, no. It has 9, yes, 1, 3, 5, 9. 7 cannot be there because its GCD is greater than 1, it's 7. And then we have 11 and we have 13. So these are the elements which are present in U14, and we are taking the operation of multiplication modulo 14 in this group. We can prove that this 3 generates this group U14 easily. Similarly, I can check 5, it generates also U14. So these are the 2 examples. If we want to check, then we can check that easily that these are the 2 generators and this is a cyclic group. Now, let us discuss a property of cyclic group, very important property. So let G be a group and let A belongs to G. If A has infinite order, then AI is equal to AJ if and only if I is equal to J. And if A has finite order, say n, then the subgroup generated by A contains these n elements, E, A square, and up to so on, A power n minus 1. And the last property in this theorem 4.1 says that if AI is equal to AJ, if and only if n divides I minus j. So this theorem has 3 parts. The first part says if in case of infinite order, this will hold. Second part says if it has finite order, then the number of elements in the subgroup generated by A will be n, and these are the elements which are contained in this subgroup. And the third property says if it has finite order, then AI is equal to AJ if and only if n divides I minus j. So I'll prove all these 3 properties one by one. So let me start with the first one. Okay. Let us start with by supposing that suppose A has infinite order. All right. So so there exists no integer such that A power n is equal to 1. So there is no integer, there is no non-zero integer n such that A raised to power n equals 1, equals E, I mean, identity. All right, so there is no such integer. Now, since in the proof we have to show that AI is equal to AJ if and only if I is equal to J. So if I take AI is equal to AJ, A raised to power I equals A raised to power J, then this implies okay, so AI equals AJ. So this implies A raised to power I minus J equals E. What I have done is multiplied on both sides by the inverse of A power J. So on this side, I get identity. On the other side, I get A power minus J, which when multiplied by A power I get A power I minus J. Which means, since we already said that there is no non-zero integer n such that any non-zero integer power of A is equal to identity. Now, since A power I minus J is equal to 0, this means the only possibility is I minus J equals 0. And similarly, the converse of this statement is clearly true, because if we have I is equal to j, then a power I will be equal to a power j. So there is no need to prove the converse. Now, let us prove the second statement. If A has finite order, say n, then the subgroup generated by A is given by this set a square, and a power n minus 1. So next, we assume that the order of A is n. So next, suppose that the order of A is n. We have a finite order element. So we will prove that the subgroup generated by A is this subgroup. We can clearly see, certainly, the elements E, A squared, and up to so on, A power n minus 1. All of these elements, clearly they belong to, because these are integer powers, so they are in the subgroup generated by A. What we have to show is, actually this is equal to this. So we have to prove the inclusion of one inclusion is clear. These elements belong to this set. So we have to prove the second inclusion, that the subgroup generated by A is a subset of this, right? So let us take any element from this set. So this is why this is clear, because these are the integer powers, and hence by definition of this set, it will belong to the set. So clearly, that means, that is, we have this set E A square, and up to so on, a power n minus 1. So this is a subset of the subgroup generated by A. So we have to prove the other side. So let's take an element. Let us take an arbitrary element from the subgroup generated by A. Since the elements of this subgroup are of the form A power k, and let us say this is an arbitrary element, is an arbitrary element of this set. Now, by the division algorithm, since we have to, yes, by the division algorithm, so by the division algo, we have, there exist two integers. There exist integers q and r, such that what happens is, k is equal to a q m plus r, with this property that the remainder r is greater than or equal to 0 and will be less than n. All right. Thus, we have taken a power k. So a power k can be taken as a raised to power k is equal to, if we just replace k by this expression, qn plus r. So I'm sorry, this is qn plus r. And if I just break down it into its factor. So I get a power qn multiplied by a power r, and this is equal to a power q whole raised a power n whole raised to the power q okay, so a power n whole power q multiplied by ar. And since a power n is identity, already supposed that the order of the element is n. So this is identity, and identity power q is identity again, and identity multiplied by ar is ar. So I'll just skip few steps. So a power k is equal to a power r, and since it is an element of this subgroup, so this means ar is also an element of this subgroup. That is what we have is a power k equals a power r, where r is greater than equal to 0 and less than n. And this means, now since r is less than n and greater than equal to 0, this means a power k is some power of a with these conditions. So it means a power k is among these elements. So a power k belongs to e a square. So it could be one of the elements in this set, because it is clear that 0 is greater than r and less than n. So a power r is one of these set elements, and a power k is among this set. Now this is the other side. That is, we have taken any element, an arbitrary element from this set, from this subgroup, and it belongs to this set. Hence, both the inclusions are true, and therefore these two sets are equal. So it is proved. From here we have seen that the subgroup generated by A is subset of set E, A square, and so on, a power n minus 1. And from these two inclusions, we have established the fact that this subgroup is equal to this set. Now, let us come to the last part of this theorem, which says ai is equal to aj if and only if n divides I minus j. And in this case, we have the order of the element is finite. So let us start with the assumption. So last, at the end, in the end, we assume that a power I equals a power j, and proof that n divides I minus j. Now observe that, again by the same method that we did, observe that a power I equals a power j. This implies a power I minus j equals identity. Again, by multiplying on both sides by the inverse of a power j. And again, by the division algorithm, again, because we already know that the order of a is finite, so a power n is equal to e. And order means this is the smallest such positive integer such that a has a power n is equal to identity. So that is why we will use the division algorithm here. because now we have another power, a power I minus j, which is equal to identity. So that is why we want to determine that what is the relation between n and I minus j. So by division algorithm, again, there exist two integers. There exist two integers, I and j, such q and r, such that what we have is I minus j equals qn plus r, where r is greater than equal to 0 and less than n. Now, if I take again, replace I minus j by this qn plus r, so I get a I minus j. By the similar argument that we used in the second part of this theorem, I get a power r. A I minus j equals a power r. Now, since n is the least such positive integer, since n is the least positive integer such that a power n equals e, with a power n equals e, and since r, we are saying what are the conditions on r? R is less than n and greater than equal to 0. So of course r cannot be less than n, and a power r is equal to a power I minus j is equal to identity. We cannot have it, right? Because n is the least such positive integer. We cannot have again a smaller integer which is whose power whose a's power is equal to identity. So that is why r cannot be greater than 0. Actually, r is less than r is equal to 0. So such that this and a raised to power I minus j equals e equals ar. So what is the only option we have? So it is only true when r is equal to 0. And what happens if r is equal to 0? If this r is equal to 0, if the remainder is 0, this means I minus j equals qn, and by definition, n divides I minus j. So we have proved one side of the theorem, that if ai is equal to aj, if and only if n divides I minus j. So we have proved if I is equal to ai is equal to aj, then n divides I minus j. Converse part is very simple. So if let's try to prove the converse. Let me write it here. Conversely, if n divides I minus j, then what will happen is I minus j equals nq for some integer q. All right. And in this case, a power I minus j will be, so a power I minus j equals a power nq. And since we can write it as a power n whole power q, and this is equal to e power q, and this is equal to e. So a power I minus j equals e, and if I multiply on both sides by a power j, then this is equal to ai equals aj. So this implies ai equals aj. So what we have done is multiplying both sides by a power j on this equation, right? So we get the desired result. So this is the end of the proof. So this is very important criteria, very important theorem property for the cyclic groups, and it has two corollaries, which is given in the next slide. And there is one important remark that I want to make. You can see that this cyclic subgroup generated by A is equal to a square a power n minus 1. So if we count the number of elements, So then there are n elements, because from 1 to n minus 1, and then 0 is another identity is a power 0. So we have total n elements here, which is equal to the order of the element. So if the order of the element is finite, then the number of elements in the subgroup generated by A will be equal to the order of the element. So this is our first corollary. See here, this is our first corollary for any group element A. The order of element and the order of the cyclic subgroup generated by that element are the same. And the corollary 2 says if AK is equal to E, then N divides K. This is very simple because we can prove it by using the last theorem statement. AK is equal to E. We have an element of finite order. E can be written as A power 0. So by the last part of the above theorem, N divides I minus J. So here N divides K minus 0. So that means N divides K. Right, so here you can see AK is equal to AE, and E can be written as A power 0. So by last part of the above theorem, N divides K minus 0. In fact, and K minus 0 is K. So this is the proof of this theorem, this corollary. And one more important point that I want to make here is that actually subgroups has all the positive and negative, contains all the positive and negative powers of some element, cyclic subgroups. But here you see only the positive powers are there. E, A power 1, A square, A power n minus 1. So actually, why is this true? Because the negative powers, if you have A power minus 1, then this is equal to A power n minus 1. So these negative powers are also here in some other in the form of positive powers. Why? Because the order of A is equal to n. So what we have is A power n is equal to E. We can write this as A power n minus 1 multiplied by A equals E, which means the inverse of A, is the same as A power n minus 1. And similarly, if I take the A power minus 2, then this is equal to A power n minus 2, which is again evident from this same definition of the order of the element. So all the negative powers are also there, but they are represented in this positive powers, in their positive counterparts. So this is the our required result, and that is the end of this video. So thank you for watching, and we'll see for the next time. Thank you.